Hi everyone. This is Chunxu. Today, my friend Beinan and I are really happy to give you folks a presentation about the metadata caching in the Iceberg connector. First of all, for the agenda of the presentation today, generally there are 4 sections. First of all, I would like to give you folks introduction about the performance bottleneck and how Presto works. Especially the performance bottlenecks motivates our work about the metadata caching in Presto. And for the second part, my friend Beinan would like to talk about the metadata caching, especially about the high-level design of the metadata caching and the 2 caching methods that we proposed and implemented in Presto. One is the caching the decompressed metadata bytes, and the other is caching the deserialized metadata objects. And also on the third section, we'll talk about some experimental evaluation of our approach, especially the 2 caching methods compared with a non-cache strategy. And finally, we'll give you folks a conclusion about what we have learned from this journey. Okay, so let's begin with some very quick introduction. First of all, I guess most of you may have already known this general architecture of Presto. So here I'll just give you folks a quick overview of it. So for Presto, mostly we have some clients, some Presto clients, like some CLI, some JDBC client, or Python client. Those clients could send some queries to the Presto cluster, usually to the Presto coordinator here. And for this node, it connects with some different metastores. Like for the Iceberg connector, the story here may be a bit different, that we support different types of metastores here, like Hive or the Hadoop catalog or the AWS Glue catalog for it, for example. And then for the coordinator node, it could generate the query plan and schedule the queries across different Presto workers. And for Presto workers, they are taking charge of the real query work, that they can query the data set from external storage, like from HDFS or say from AWS S3 or from Google Cloud GCS buckets. And then those Presto workers will open the files, parse the files, and get the necessary data and return it. There will also be an aggregation step, finally, for the query result, and then return to all the Presto clients. So OK, so why we would like to have a metadata caching? So the case for Iceberg connector is that for Iceberg, it is kind of a table format built on top of some data lakes. And in the data lake, usually we use different column-oriented file formats here, like Parquet or ORC. And for these types of file formats, usually the data is organized into columns. So say if the data belong to the same column, they are stored usually closely to each other. So to read the information from the data files, usually we also want to manage the group of rows that will help us to manage the data files. So for example, we have some footer and index information stored in those data files. And then this type of information could help us to escape unnecessary rows, especially when the predicate pushdown strategy is enabled in Presto. But here's an issue for it. Say, from what we have learned, that is, for example, here's a report that reported by some meta engineers, that we observed that the data pathing could become a performance bottleneck in the Presto query. Say, take this diagram as an example. So on the bottom, there is a read strap function, which is used to read a strap and ORC file. So that's the kind of thing that we want to read the file and pass the file. And here, to achieve that mechanism, there's a very long bar here. So a very long bar here, which is about pass the stripe footers, etc., etc. So those are the steps used to pass the metadata of the data file. So from what meta engineers have reported, they noticed that like 30% of CPU is spent on read the strap. So that's a very large issue that it significantly blocks them from even larger Presto clusters. So that's why we would like to propose and implement a metadata caching layer into the Presto structure to solve the problem. So next, Beinan will talk more about the high-level design and implementation of this mechanism.
Thank you, Chunxu. Yeah. I'm Beinan, engineer from Alluxio. Today we will share something about our implementation on the metadata caching on Presto DB. Okay, so here is the current architecture of the Presto plus Alluxio local cache. The Presto local cache, we also call the RaptorX project. We are seeing this cache can make Presto DB 10 times faster on some particular query or database, because in the Facebook, they have some data set called Raptor. Then we have RaptorX. If you are using local cache for the dashboard queries or some query, we can see a super high cache hit rate, maybe more than 97%. So we can see here, we are making something like a 1 megabyte cache, 1 megabyte page to cache the data. But the thing here is, we are trying to make it, when we are trying to make it more faster, we found the Presto is more like a CPU-bound application. So even though we put every cache data in the memory, we can still, speed up Presto DB further. So we are thinking about what's the next bottleneck. Just as Chunxu said, we are seeing some bottleneck on the packet or awk file passing, especially for the metadata, because Presto DB is using the metadata. The metadata here is not the metadata in the higher meta store. It's the metadata stored in the packet or awk files. We are seeing Presto DB actually, they read this kind of data very, very frequently, because for most every file, it will check the metadata first. By checking the metadata, maybe check some stats or something else, the Presto will know if this data file is needed or not. If it's the data file needed, it will do some real data scan. If the entire section, maybe strap or something is not needed, it will scan the entire section. So, which means if we can put a metadata cache separately, just like here, firstly, we can improve the cache hit rate of this kind of metadata. Because for some company, because in the Facebook, the cache hit rate is super high, just because the Facebook, they have a, they have a router in front of a Presto DB cluster. So they can make each cluster, DB cluster, only handle just a couple of tables. But for other companies, they may have to have unified names, unified cluster to handle all the queries. So in this case, we might see lower cache hit rate. So that's the first reason why we want to put it separately. Then we can have a much higher hit rate just for the metadata. And the other reason is, because for the data, it's super easy. We just cache the bytes. But for the metadata, we prefer to cache some structured data, which will make the Presto DB can consume this kind of data much more easier. Yeah, let's go to our first cache approach. I think that this one is something we made last year. We just extract the metadata, the bytes of the metadata from the packet or awk files, and we put it in a separate key value store or something. And when the packet or, let's put it this way. For the first time, the awk file or packet file got read or passed, we will check the cache. If it's not there, which means the first time, right, we write the bytes, just the bytes of the file metadata, the straps metadata, or the index bytes to the key value store. It can be in memory. It can also be NVMe. We strongly recommend this kind of thing in NVMe. Then you can have a much better capacity. But in the memory, it's also okay, because as I said, the metadata is just a small portion of your data file. And when the Presto query hit the same file or the same section again, it will hit the cache. And the cache will return the bytes. And then the Presto packet or awk reader will do the deserialize. Deserialize this object, and put them into some real Java metadata object. So the remaining logic is still there. The scanner, the filter, just push down the operator to the reader and to read this kind of files. Nothing different. The only difference is by passing the entire file or extract the metadata, it can check the key value store. Because each kind of is metadata, we can very easily to get a unique key. The metadata, if you're familiar with the awk or parquet, for each section, you can just have a very unique key for this kind of value. Now, here is the first approach. We cache the bytes, the raw bytes. We just, the byte is not the structure object. And, but we found, okay, the CPU is still bottleneck, right? So then we have the second approach. Yeah, this one. Here's the thing. So we still need to extract the data. And when we extract the data, I mean the bytes, we just follow the previous approach. We deserialize this kind of object to the Java object. Here is just what we can consume, what the Presto DB consumed. I think the first version of cache tool, we just put this kind of thing in the memory, in a Java hash map. I think that's the work contributed by Rongrong early this year or last year. But if we put a lot, maybe millions, billions of objects in the memory, we see a lot of GC pressure. It's too much. It's too much for Presto because all this kind of thing, if we put it in memory, somehow it's a long-lasting object, and the G1 GC will put it to some old generation or somehow. It's not so easy for Presto DB or for JVM to collect this kind of thing from them, to recycle the dates. So we are seeing to use some off-heap or some storage to keep this one. But in this case, we need a better encoder of the serializing or deserializing approach. We call it byte buffer. Now we're just using the flag buffer, which is also used in Arrow format for their metadata. So we use flag buffer. It's much cheaper. We can say deserialize or serialize or encode or decode implementation. They won't have allocate more memory. They just do the deserializing in place in the memory. It's super efficient. So we are using this one. We do some benchmark here. We found this one, that the flag buffer, sometimes it can be 30 or 100 times faster than the protobuf. The protobuf is the format used in the packet or files for the metadata. So we store this kind of flag buffer into the key value store. It's a little bit larger. It's actually larger than the raw bytes, but we still have some value. And when we hit the cache again, we will load this flag buffer from the cache, and the cache, when this flag buffer loaded, we will do some decode, and we will get the metadata object again, and it will consume the scanner. The thing is, this one is actually not the original Presto metadata object. It's something new. It's the flag buff object. It's a little bit different. So we changed a little bit on the scanner and the filter. That's why we didn't merge it to the Presto master, because we have a better plan. We don't want to this kind of thing merge to master. But just by our experiment, we can see more benefits, more CPU. We will reduce the CPU usage by this approach, the master tool. We will share the experiments result very soon. Yeah. So here is we caching the structured object, but it's deserialized or serialized or encoded by a much cheaper flag buffer, and we put this flag buffer in the cache. Okay, let's see the evaluation. Okay, we just want to make our experiment to be repeatable and fair enough for most queries, so we use the TPCDS query. we just use the first 10 TPCDS query. I think this can cover, somehow it can cover the typical scenarios of your dashboarding query, reporting query, interactive query. Somehow it cannot be exactly the same as your production load, but this query can show the difference. So we just monitor, collect, and report the metrics related to the CPU usage because, as Chunxu said, the bottleneck actually is on the CPU side, so we more focus on the CPU. And the Presto actually they are running the query in parallel, right? Which means the query will split to multiple splits, and this kind of splits will start it in multiple workers. So if we just compile the wall-to-wall time, sometimes it's not fair enough to do for the evaluation. So we check the CPU time because CPU time is the total CPU usage of all the splits. The Presto will sum them together. So we are using these metrics to evaluate our work. Okay, here's the most interesting part. That's one of the most interesting. This one is the second interesting one. It's the write performance. The write performance means the first time. If the first time we are seeing this kind of data, we need put this data into the cache. So, which means that's the overhead of this two approach, right? So because you are doing something extra, you need to write data to your disk or to your memory, right? Before the cache, we don't need to do anything. We just deserialize the object and read it. But for this time, we need to put the data into the disk or somehow. So we can see the overhead. The overhead of the method 1 is just for the 10 queries. Mostly it's just about 10 to 20%. We are seeing the 10 to 20% latency increased. And for the second approach, we are seeing a little bit more, from 10 to 30, because we are doing something for the decode and for the encode. We need flat buffer to encode the value. We can see it's quite consistent, right? Maybe we can see some overhead there. But it's not too much. I think it's acceptable.
Can you comment on what the y-axis is?
Oh, yeah, that's a good question. Good one. Yeah. So here is the 10 query, yes. The QI, and this is the CPU time. Oh. Or the CPU time, as I mentioned, right? We are watching the CPU total CPU time of this query. Yeah. So we are seeing more CPU time here.
Higher is worse.
Yes, higher is worse. Exactly. Higher is worse. Yes. True. Yeah, we are seeing some increase, right? Increasement for each query, almost, right? Because that's the overhead of writing data into the cache.
Yes.
Yeah. Yes, the next one is our benefit. It's our benefit, right? So we are seeing the latency got decreased because we are hitting the cache. We are loading the data from the cache, and the cache is much more faster, and it might be more convenient for the Presto to consume. We can see for some of the query, we are doing really good. Because for this kind of query, I believe, because the Presto query, they won't read everything from the data file. Most of the query, as I said, they will just check the metadata. If there's nothing we want there, we just skip the entire file, right? So we can see it's a lot of improvement for the query 1, query 2, query 3. Query 3 maybe just okay. And then for some query, maybe we are seeing a little bit slower because maybe the cache is not working well. But for the query 9, it's an exception. For this query, we did see for either method 1 and method 2, we thought we are to make things worse. I checked the metrics of the query stat, of the runtime stat is this one. Actually, we are seeing, because this is the query 9, if you check the SQL, it's super complicated. They have 14 or 15 stages. They are drawing the same table again and again, I think 10 times or 9 times. And, but even this very complicated query, we are still seeing, we are speeding up the table scan because they by using the cache, we can still speed up the load, the metadata or something. But why is we are seeing the bad results for this one? Just because we are seeing for some scheduling time got increased. I guess maybe we are using more resource, maybe we are occupied more memories or something, which make the Presto DB worker feel really bad. He may think, okay, I don't have any resource to handle your splits or something. Then we are waiting for resource or something. Because we're still not quite sure. This is just our recent work, so we are still doing the investigation about this one. But here I just want to talk about it. The table scan is still speed up, but somehow the schedule time get much longer. So we are getting a worse performance. Okay, so let's talk about a little bit about what we have learned for this work. Firstly, we think if we cache some metadata, if we just cache the raw bytes, the bytes, we can have a minimal performance overhead during the cold start, which means if the cache data is not in the cache, the overhead of the actual work we need to do, we can just cache the raw bytes. I think that's aligned with what we have seen for the local cache, because for local cache, I mean the Raptor X project, we just cache the raw bytes, and yeah, we are seeing we have some overhead, maybe 10% or 20% of overhead for the caching, just for the cold start. And if we want to do something better, if you are seeing your Presto cluster is CPU bounded, you really need some more CPU or something. You can try to cache the deserialized metadata object. You can put it into the flag buffer or something else. This one can significantly improve the CPU consumption when the cache is warm. But again, if the cache is not warm, the data is cold, you will see more overhead. But again, all the feature I'm talking about is still under the development. We are not merged to either Presto or Alluxio masters. We are still working on it, and we will make maybe a formal release or something later, maybe next year, early next year or something. And we may have a better off-heap cache solution, or maybe a better native support for this feature. Okay, I think Chunxu and I are done.
I probably have many questions. The question number one, I'm sorry, I do apologize. Maybe I missed the beginning of your presentation. And what are challenges actually you have experienced with the existing caching solution, which is a Raptor X? So Raptor X allows you to cache all these headers and footers of Parquet and ORC files already, but it's on heap. Yeah, I know that. Can you tell me?
It's what? Yeah.
No, it doesn't parse. It's a Java object. Because
I'm just talking about from this one. We are seeing two kind of performance issue. The first one is this one. We are trying to speed up our I/O by using local cache, but we are seeing the CPU usage is 100%. And by checking this flame chart, we are seeing a lot of CPU is just on the stripe or the metadata passing. That's the first one. And by having this one, we are trying to allocate a large in-memory cache. We just want to cache the object. That's just the current metadata cache or some called fragment cache in Presto. If we put all of this kind of thing just in memory with the raw object, just the object, the Presto object, we are seeing the GC is overwhelming the JVM for the GC, because if we have more than 10 gigabytes or 20 gigabytes objects in the memory, the GC priority is super high, because it's just a long-living object in JVM. I think that's the issue why we need to involve this two-cache approach, because we need to make something off-heap. We need to put something into the disk.
Yes, you just answered partially on my question. So the on-heap cache for the footers and headers of the parquet and RC files doesn't require you to parse data because it's Java objects already. So you don't need to parse anything.
Sure.
So it's a minimum CPU consumption.
Yes.
Another other issue I don't understand, of course, because the size of the on-heap cache, it can become a bottleneck. But the question is, what actually do you observe in a real application? So what are the size which is required to cache all the parquet or ORC headers and footers and indexes? Because usually it's less than 1% of the file, and if you like handle 1 terabyte of data per server, it's 10 gig maximum. Probably much less than 10 gig.
I'm not sure I can share the real number of data, but I can see, I can share what I have.
I thought that you just have some answers. Okay, we just run some application with customers. They just require 20 gigabyte of heap memory to store everything, and it doesn't work as we expected.
Yes. I think I can say something about the Meta use case because they are using the Raptor X. As I said, they have a router in front of the Presto cluster. They will routing the query to each separate cluster by the table, by the data set. So which means for each Presto cluster, they only handle a small set of your working set, right? So it's maybe just 10% or maybe 5%. So in this case, they really don't need a large number of metadata cache. They can just use a very small, maybe 10 gigabytes or something. Well, I think they use a very small metadata cache. It can handle the case. But for some other companies, they are using just one Presto cluster to handle everything, every table, and handle the entire Hive data warehouse. So in this case, I don't know how much memory, because we don't have an evaluation for the working set. It should be super large, because every data, if you go through the Presto, if we need to cache it, it will be a large number. Even though maybe just 1% or less than 1%, it's still a large number. We cannot just put it in the memory.
Yeah, sure.
It depends on how you use Presto.
And then just one more question. So you store the data into Kiwi store, such as like RocksDB or some other Kiwi stores, but this is a store, it's not a cache.
We have we have 3 implementations of the Kiwi store. The first one, the second one, just as you said, it's RocksDB. We are using RocksDB. But I don't think the RocksDB can give you the best performance. So mostly, I think most of our users are just using our very simple key value store. Just keep the key value pair on your NVMe. It's a local file-based key value store. Just the key is the file name, value is just the content of this file. It's not super efficient, but it's simple. It's simple and straightforward. And the other is some of our users, they are using the in-memory, in the heap, the key in the heap, but that's the same thing. If we are using the cache in the heap, we will see a lot of GC issues. That's not something I recommend here.
Thank you.
So all your timings were given with CPU time. I'm just wondering, I know you commented on that earlier that you were going to use that as opposed to wall clock time, but I was sort of hoping you'd show both. Because, I mean, CPU time can be not indicative of how it affects the query. And so one might assume that might have been chosen for that. So can you comment on wall clock time? Because I mean, that has to do with how parallelism affects your caching techniques.
I don't really think that the parallelism will get some real affection to impact on our cache because we just have a very lightweight log on our key value store.
I mean, was wall clock time looked about the same on those graphs, or I mean, I wish you would have had.
Yeah, you're right. We checked about wall time because when we collect the CPU time, But we do some a little bit of benefit. It's much smaller than the value I show. I have to say because if it's in parallel, that means the benefits will be divided by your thread number. Am I right? So we see very few, maybe 1%, 2%, or maybe something just on par. Yeah.
Yeah.
But if we are talking about the throughput of your entire Presto cluster, they still have some benefits. They can save your CPU resource.
Yeah, I think in general, we can collect more metrics related to it and report to folks. Yeah.
I have a question. So how do you ensure consistency between your cached data and data in storage?
That's really a good question. I think there's some Uber guys that sit here. We are working together for this one. I think the Kurt or Leontre is here. The most simplest way is when we do the planning, we will list all the files in the directory, right? So in this case, we will get the metadata of each file. And in the metadata, we can have the last modified time of this file. Okay, the Presto will pass this last modified time from coordinator to the workers. And for the worker, when they check the data in the cache, it will compile the last modified time from the list and the last modified time of the file we cached. If it does not match, which means the data we cached is stored out of date. We just need to do some eviction. We will delete the data. But we have a better solution, a more simple solution actually from Uber. We just put the last modified time with the file path. We combine them together to do an MD5, which means if the last modified time got changed, it won't hit the old cache. It will have a new cache key, right? And it will try to generate a new entry in the cache. And the next time some guy reads the same data, it will read it from the new data. Yeah, that's a two approach.
But you still need to evict the old data. Is that just off of LRU or what?
Yes, exactly. Yes, we have the LRU, so the old data will get evicted somehow later. Yeah. But it's still there. Somehow we are wasting some. Yes, consumer resources. But if the got changed, we won't touch it anymore. So somehow maybe 1 hour or 1 day later, it will get evicted. But if we store the last modified time on our cache, which means we may need more log on the file level. We do see some performance penalty because we are keeping more data. Yeah, and because we will load the data from the cache, we need to pass another field. Yeah, a little bit, not very much. Okay, so.
Yeah. Yes. Yeah. You mean that the write is async or not? Yeah. Yeah. For the rest of the cache is async. We have two approach. We have a switch actually. The first one is just synchronize the write. We just wait for this one we are based on non-async approach. So we will wait for the data stored or read to the disk, and then got returned. As that way we see a CPU time go longer. But we also have an async write. We have a thread pool, and it will put this write into the queue, and it will handle the async write. But when it's not for metadata cache, it's for the data cache. When we try the async approach on Facebook production, we are seeing a lot of, the queue is full, or some exception, which means the data you want to cache cannot get the resource to really land it on your disk. So just recently, I think some contributor from DD, they make a contribution which makes our async approach have a fallback. So if there's no CPU resource or no thread to handle the queue, we just fall back to a synchronous way. So I think that might be a balance. But the total CPU time, you may see the difference, but I didn't check that. Yeah. Yeah. I think, yeah. That's all for us today. Thank you.
Thank you.